This is Lecture 6, the final lecture of the Quantum Formalism Differential Equations Review Lectures. Today we'll be discussing power series solutions. So to start off, we'll review some power series terminology. So a power series will converge or respectively diverge if the sequence of partial sums, this sequence, converges or diverges. So here you're doing a finite sum with capital N terms, and then looking at the limit as the number of terms in your sum goes to infinity. So another way to see this, to look at this, is the series will converge if the sort of tails of all these partial sums goes to 0. So that would be sort of the sum where you start at capital N and then look at all the remaining terms. These need to go to 0 as capital N goes to infinity. All right, and then another term is a power series will converge absolutely if the series where you replace all the terms with their absolute values, if that one converges. And if a series converges but it does not converge absolutely, that's said to converge conditionally. All right, there's also something called the radius of convergence, which we'll use this Greek letter rho for, between 0 and infinity, and it can be 0 and it can also be infinity, such that your series will converge absolutely when the absolute value of x minus x0 is less than rho, and diverges when x minus x0, the absolute value of x minus x0 is greater than rho. So you have an interval where you know that it converges absolutely, and then outside of, on the open interval outside of that, it diverges. But there will be 2 points where the absolute value of x minus x0 is equal to rho, and it's not clear exactly what will happen. So when you're at these 2 points, the boundary points of this interval of convergence, anything can happen. So all 3 possibilities could either converge conditionally, converge absolutely, or diverge. All right, so that's a nice feature of power series. If you figure out this number rho, then you know most of the convergence behavior of the series. All right, you can do various operations on power series as well. You can add 2 power series together, multiply 2 power series. And you can also divide 2 power series as long as you're looking away from any zeros in the denominator power series, and you will get another power series when you do that. So that's pretty useful. And for addition and multiplication, you actually know that the radius of convergence of your new power series will be at least as large as the minimum of the radii of convergence of the 2 power series you're adding or multiplying. Another useful fact for differential equations purposes is that you can differentiate power series. They will be differentiable. And you do that term by term. So it's pretty straightforward. You differentiate just as if it were a polynomial that had infinitely many terms, more or less, right? So this monomial term, an x minus x0 to the n, you just do the derivative of that. So it'll be n times an times the quantity x minus x0 to the n minus 1. And because you can just keep doing this term by term differentiation forever, power series will be infinitely differentiable on their interval of convergence. So I guess if rho is equal to 0, if the radius of convergence is 0, then you'll probably have some problems. But in that case, yeah, the power series isn't going to be super useful because it'll only be defined at a single point. So that's not too good. All right, you can also read off the coefficients of your power series from the derivatives. Namely, if you take the nth derivative, plug in x0, and then divide by n factorial. That will give you the coefficient of the nth term, an. Which you can see pretty readily, right? Like if you take the very first term, that will just be, the constant term is just a0. So, all right, the 0th derivative, you don't really need to bother plugging in anything. You plug in x0, and then all the other terms will go away, and you'll just get the constant term a0. Then the first term is a1 times x. If you take one derivative, you'll have an a1 there, and then all the other terms will have powers of x minus x0. So if you plug in x0 again, those will all go away, and you'll just get a1. And then the next one would be like a2 times x squared. And now when you take two derivatives, you're going to get this 2 coming down from the exponent. And so that repeated differentiation is what makes this n factorial appear. All right. So every power series is infinitely differentiable, and you have this formula for the coefficients. On the other hand, you can start with a function and then use this formula to produce coefficients for a power series. And then the question is, will this power series actually have a positive radius of convergence, or will it only converge at x equals x0, right? Obviously, every power series will converge at least at the point x0 itself, because then you're just going to get whatever the constant term of your power series is when you plug in x equals x0. So that's fine. But for it to really make sense as a function, at least in some small interval, you need to have a positive radius of convergence. And so you're not going to be able to do any of this differential calculus unless you actually have a positive radius of convergence. All right, so yeah, if you have a Taylor expansion like this that actually does have some positive radius of convergence, then your function is said to be analytic at the point x0. So more or less, that's just saying that your point has that your function does equal some power series on some interval around x0. So obviously, all power series with positive radii convergence will be analytic. But this will also apply to lots of other functions we know, right? Like sine and cosine, e to the x, all these things. Those are all going to be, well, those ones are all analytic everywhere even. Of course, any polynomial will be analytic as well. All right, so the ratio test is pretty useful for figuring out the radius of convergence. So namely, it gives you this formula that if this limit an divided by an plus 1 absolute value as n goes to infinity exists, then that will actually be equal to the radius of convergence. And if you reverse the fraction and that limit is equal to 0, then that tells you that the radius of convergence is infinity. So a quick example of that is this series with coefficients 1 over n. So now if you look at this limit, the coefficient for an is 1 over n, so the coefficient for an plus 1 is 1 over n plus 1. You divide those. Dividing those two reciprocals is the same as dividing n plus 1 over n. And then that, of course, has a limit of 1 as n goes to infinity, right? Because this thing is equal to 1 plus 1 over n, and then 1 over n as n goes to infinity will go to 0. So that tells you that the radius of convergence is 1. And then, like I said before, so you know that it converges absolutely on the open interval between -1 and 1, and it'll diverge outside of that. And then, as I said before, the behavior at -1 and 1 could be anything. In this case, it'll diverge for x equals 1 and converge conditionally at x equals -1. Right? I mean, it can't converge absolutely, because if you put absolute value bars on the series with x equal with -1 in place of x, you'll just get the series with x equal to 1 instead, and that one diverges. All right. So now let's talk about how to use power series in order to solve differential equations. So we're going to be in the same sort of regime as we were in the previous few lectures. So we'll be looking at second order linear homogeneous, in this case, differential equations. For these power series, you actually don't usually want to bring them into standard form, at least as far as like finding the solutions goes, especially if you have something like a polynomial for capital P of x and something for Q of x and something for R of x, because then if you go and divide by capital P of x, you're going to get sort of complicated power series for the new coefficients. But if you just left the polynomial there in front of the y double prime, then things will end up being pretty simple. So you usually will want to leave things alone rather than dividing by capital P of x. Unless it's going to make the differential equation simpler for some reason, or the power series you get for the coefficients simpler for some reason. But usually we'll end up making it more complicated. All right, but anyway, as far as analyzing the behavior of the power series, you do want to look at the standard form coefficients. That would be capital Q of x and capital R, capital lowercase p of x, which is capital Q divided by capital P, and lowercase q, which is capital R of x divided by capital P. And a point x0 will be called an ordinary point if those standard form coefficients are analytic at x0. So remember, that means they have to be equal to power series with a positive radius of convergence. And so we'll only talk about power series solutions at ordinary points in this lecture, but it is possible also to find power series solutions at what are called regular singular points, using something called the method of Frobenius, which is a similar power series solution method. But I won't talk about that here. Right, yeah, so if you're not an ordinary point, then you're a singular point, and then there's a certain class of singular points called regular singular points, where you're also able to do power series solutions. But we'll just focus on ordinary points for now. All right, let's start with an example. So let's try to find some power series solutions to this differential equation, y double prime plus y equals 0. So we do know how to solve this one already, right? The characteristic equation, this is just a constant coefficient equation. The characteristic equation is r squared plus 1 equals 0. The roots are plus or minus I. So we know that the general solution is just c1 cosine x plus c2 sine of x. All right. So let's see if we can produce that same general solution using power series methods, just to see how everything works. All right, so we start off assuming that y is a power series, and we're doing power series solutions at the origin. So that means x0 is equal to 0. So in those power series expansions, we'll just start with y is the sum of an x to the n. All right, and then we have term-by-term differentiation. So y prime will be the sum of n an x to the n minus 1, and y double prime will be the sum of n times n minus 1 an x to the n minus 2. All right, so we plug this one in for y double prime, and we plug this one in for y. All right, so now we're going to try to combine these two power series into a single power series. Right, I said that if you add two power series or multiply two power series together, you should get another power series when you do that. So let's see how that works. And what you need to do in order to add these two together is you need to make sure that the powers of x line up. So here we have an x to the n minus 2, and here we have an x to the n. If we had the same exponent there, then we could just add the coefficients to add the two series together, which would be good. All right, well, that's easily fixed. We'll need to re-index the series on the left, the series for the second derivative. So we'll use this formula, m equals n minus 2, or in other words, n is equal to m plus 2. So whenever we see an n, we can replace it by m plus 2. And whenever we see an n minus 2, we could replace that with m. So yeah, so now we've gone from an n minus 2 into the exponent into an m. So that's looking closer to what we have in the other series. All right, so n times n minus 1 will become m plus 2 times m plus 1. This n will become an m plus 2. And now the bounds on our series, we started at n equals 2, which would be the x to the 0 term for the series on the left. So we will start at m equals 0, because now our exponent is m. So we're starting with a constant term in both cases. Or you could use the formula m equals n minus 2, so that if you start with n equal to 2, subtract 2 from that, that should mean m is equal to, starting at m equals 0. All right, so now the two series have exponents that more or less match up. They just have different letters, but that's okay, because this is just notation. We can change from the letter m to the letter n with no issues at all. That doesn't actually matter, right? M is not a variable or anything. It's just part of the notation for the sum. This is just saying that you should plug in m equals 0 and then plug in m equals 1 into this formula and add those things together and so on up to infinity. So if you call m and n, if you switch the name from m to n, it does nothing. So we could have done that at the beginning. There wasn't necessarily a reason to introduce a new letter. I just thought that for the first time we were reindexing a series like this, I should use a new letter just to be clear. But we're immediately going to switch back to the old letter now. All right, so going from here to here, we were reindexing. Here we're not doing any reindexing at all. We're just switching the name from m to n. So this reindexing now is just m is equal to n. All right. So now the two series have the same exponents. They're both looking at x to the n, and they're starting at n equals 0 and going to infinity. So now we can just add the coefficients together in order to add the two series. All right, so we produce this big power series for the left-hand side of the differential equation, and that should be equal to 0. But it's supposed to be 0 as a function, and so what does it mean for a power series to be equal to 0 as a function? Well, actually it means that all of the coefficients have to be equal to 0, right? We had this formula for the nth, the nth coefficient of a power series is the nth derivative at x0 divided by n factorial. In this case, x0 is 0. And when you take the 0 function, no matter how many derivatives you take, and no matter what you plug in, you're always going to get 0. So that formula will say that all the coefficients of the 0 power series have to be 0. All right. So that tells us that this expression in parentheses has to be equal to 0 for all n. All right, so this gives what's called a recurrence relation, which is something that will allow us to determine future coefficients from the previous coefficients. Right, so we get this formula. So this is setting this whole thing equal to 0 and then solving for an plus 2. So we subtract an to the other side and then divide by n plus 2 and n plus 1. That has to be 0 for all n greater than or equal to 0. And so this allows you to determine the an plus 2 coefficient from the an coefficient. So if we start with some coefficients, then we can produce all of the future coefficients of the same parity. So starting from a0, we can produce all the even coefficients just by applying this formula over and over again. And starting with a1, we can produce all the odd coefficients just by using this formula over and over again. All right, yeah. So a0 and a1 can be arbitrary. We don't actually have any constraints on those, right? They can be whatever, but once we have a0 and a1, all the other coefficients will be pinned down just by applying this formula a bunch of times. All right, so let's do that. So starting with a0, then we can get a2 by using this formula with n equals 0. So then in the denominator, we will have 2 times 1. So A2 is minus A0 divided by 2 times 1. Then to get A4, we plug in the formula with n equals 2. So we'll have A4 is minus A2 divided by 4 times 3. But then we can plug in this expression in the place of A2. And so that gives us A0, positive A0, because the two minus signs cancel out, divided by 4 times 3 times 2 times 1, which will be 4 factorial. And then similarly, right, we'd have a formula for A6, which would be minus A4 divided by 6 times 5. And then that would give us negative A0 divided by 6 factorial. All right, so we can see we're just going to get a pattern, right? Any even coefficient will be equal to some power of minus 1 times A0 divided by that number factorial. So A2k will be minus 1 to some power times A0 divided by 2k factorial. And the correct power, we want this to be equal, this should equal just A0 when k is 0, right? And so that means it should be minus 1 to the k power rather than like minus 1 to the k plus 1 power. Right, you're going to get, the minus signs are going to alternate every time because of the minus sign in the formula. And so it should start at positive 1 and then switch to minus 1 for the k equals 1 case, right? The k equals 1 case is this formula for A2, which does have a minus sign. Okay, and then similarly, you'll get a very similar formula for the odd terms, right? A3 will be minus A1 divided by 3 times 2. And then A5 will be minus A3 divided by 5 times 4. The minus signs will cancel out, and you'll get A1 over 5 factorial. And so on. So the A2k plus first term, so this will include all the odd terms, will be minus 1 to the k times A1 divided by 2k plus 1 factorial. So here, this should equal A1 when k is 0. So we don't want a minus sign when k is 0. So that's why we have a minus 1 to the k rather than minus 1 to the k plus 1. And again, the signs will alternate every time as you proceed to the next consecutive odd integer. So something like that is the correct formula. Okay, so now we can just plug in these coefficient formulas into our generic power series to produce power series solutions for y. So it'll be A0 times the sum of all the even terms, so k from 0 to infinity, minus 1 to the k, x to the 2k over 2k factorial. Right, this is the 2kth coefficient, so it should accompany the power x to the 2k. All right, and then similarly, all the odd terms will have a factor of A1 that we can pull out, and then we'll have minus 1 to the k, x to the 2k plus 1 power divided by 2k plus 1 factorial. But you can recognize these are exactly the Taylor series for cosine of x and sine of x, right? This one is cosine of x, and this one is sine of x. All right, so that's exactly what we should be getting, right? We knew the solution to this equation already. It's some constant times arbitrary constant times cosine x plus some other arbitrary constant times sine x. And so that's what we got. And in this case, those arbitrary constants are actually the power series coefficients for our power series solution, right? The coefficient in front of cosine x is the constant term of our power series, A0, and the coefficient in front of sine x is the constant term of our power series, A1. And it turns out those power series coefficients can be arbitrary. This should always be the case, right? Because we know that for a second-order linear differential equation like this, every initial value problem should have a unique solution, right? An initial value problem at x0 will look something like y of 0 equals some number, and y prime of 0 is equal to some other number. But if you remember the power series coefficient formulas, I mean, you don't even need to remember them. You can just look at a power series written down as just, starting as A0 plus A1x plus so on. a0 is exactly what you get when you plug in x equals 0. So this a0 should be this y0. And then a1 is exactly what you get when you take a derivative and then plug in x equals 0. So this a1 is this y prime 0. So if you're not working on an initial value problem, if you're trying to find the general solution to some linear homogeneous equation like this, a0 and a1 will always be arbitrary, because you're supposed to be able to solve every initial value problem. Every initial value problem like this should have a unique solution, so no matter what a0 and a1 are, you should be able to get a unique solution. Okay. So it's not too surprising that these a0 and a1 are like popping out as arbitrary constants in our general solution formula. All right, now let's try an example that we don't already know how to solve. So now, rather than constant coefficients, we've got a coefficient which is minus x, so y double prime minus xy equals 0. This is a physics equation called the area equation. I think this is like a very simple case of the Schrödinger equation, if I remember correctly, something like that. So I think it's the Schrödinger equation, the time-independent version with some kind of simple potential well that I don't remember off the top of my head. Anyway, not super important. So again, let's use our formulas for the general power series for y about the origin and its second derivative. So this is the same formula as we used in the last example. This time we have this coefficient of x, but that's not too bad. So to multiply this power series by x, all we do is just add a 1 to all the exponents, right? X to the n times x is just x to the n plus 1. So we've just incremented the exponent by 1 there in all the terms. All right, so now again, to add these two together, we should reindex. I chose to reindex both series to just use x to the n, but you could just leave one of the series as they are and then reindex the other series to match it. It doesn't really matter too much. All right, yeah, so I reindexed this one so that the new n is equal to the old n minus 1. So here I'm not bothering to like switch to m and then switch back to n. I'm just going right away from an n in the first series to a different n when I reindex, but it doesn't make a difference because again, the name of the indexing variable has no effect whatsoever on what's going on. All right, and in this one, the new n is the old n plus 1. All right, so this is exactly the same reindexing that we had in the previous example. So the old n becomes a new n plus 2. So we'll have an n plus 2 times n plus 1 times a n plus 2 x to the n. And before we were starting at n equals 2, which was the constant term. So now we're starting at n equals 0, which is the constant term. For the second series, the new n is the old n plus 1. So the old n here will become the new n minus 1. And then x to the n plus 1 will become x to the n. This time, we were starting at n equals 0 in the old series, which was the x to the first power term. So now in this new reindexed x to the n series, we should start at n equals 1. All right, so now the exponents between the two series will match up. We're dealing with an x to the n for both of them, but the number of terms is not the same. The series on the left starts at n equals 0, and the series on the right starts at n equals 1. So we can't just combine the series right away, but there's an easy fix. We just have to peel out the n equals 0 term from the first series. So we plug in n equals 0 into this series on the left, and we will get 2 times 1 times a2 times x to the 0. So that's the constant term of this series. And so if we pull out the constant term, now we can start at n equals 1 instead. All right, now both series, we're working with x to the n. Both of them start at n equals 1. Now we can just add the coefficients together. All right, and once again, we need all so now we have a big power series on the left, and once again, we need all coefficients to be equal to 0. And so that will give us, first it will give us that A2 has to be 0. That's from setting this one equal to 0. And then from setting this coefficient these coefficients equal to 0, we'll get a recurrence relation. All right, so we'll end up with A2 is equal to 0, and this recurrence relation, an plus 2 is equal to an minus 1 divided by n plus 2 times n plus 1 for all n greater than equal to 1. All right, so now we can determine the coefficient that's 3 terms down the line from a given coefficient. That's still okay. We still will be able to get all of the coefficients because we also know that A2 is equal to 0. So that will allow us to get all the coefficients. So we'll start with an arbitrary A0 and an arbitrary A1, which, like I said when we were doing the previous example, just because of the existence and uniqueness theorem, you know that A0 and A1 will always have to be arbitrary if you're trying to find the general solution. Then A2 is determined, it's equal to 0, and then we can go 3 coefficients into the future using this recurrence relation. And this will allow us to get every coefficient. Okay, so first we start with A2. Then 3 coefficients later, we will have A5, and that should be equal to A2 divided by 5 times 4. So this is plugging n equals 3 into this formula. And because A2 is 0, that tells us that A5 is 0. All right, and now we can just keep going that way, right? 3 coefficients later, we'll get to A8. That should be A5. Oh, sorry, I put 5 times 4. Oops, typo. This is 8 times 7, right? My bad. Doesn't matter. It's 0 divided by something in the denominator, so who cares? We're getting 0 again. All right, so this is saying that all coefficients that are 2 modulo 3, if you want to say it that way, just, anything that when you start at 2 and repeatedly add 3, anything of the form 3k plus 2, those coefficients will all be equal to 0. All right. You can also start at this arbitrary A0 and then produce all the coefficients that are divisible by 3 using that formula. So starting at A0, A3 will be A0 divided by 3 times 2. A6 will be A3 divided by 6 times 5. And then you can plug this in the place of A3. So it'll be A0 divided by 6 times 5 times 3 times 2. And so unfortunately, we do not get a nice formula for that. It's not 6 factorial because we're missing the 4, right? 6 times 5 times 3 times 2 is not quite 6 factorial. And just missing a 4 wouldn't be a huge problem, except it's not just the 4 we're missing. We're going to continually miss a number every time, right? The next one will be A9 divided by, A9 should be A6 divided by 9 times 8. That's plugging n equals 7 into the formula. And so then when we plug in our formula for A6 into that, we'll have A0 divided by 9 times 8 times 6 times 5 times 3 times 2. So now we're missing 7 as well. So you're missing 7 as well as 4, and there's just no nice name for that function that, is multiplying 2 consecutive integers and then skipping 1 and then continuing that pattern. So the best you can do is write down something really messy like this. So A3k will be A0 divided by this messy formula where you multiply consecutive integers and then skip 1 and then keep going all the way down until you get to 2. All right. And we'll get something very similar for the terms of the form A3k plus 1. So here we'll start at A1, which is arbitrary, and then A4 will be A1 divided by 4 times 3. A7 is A4 divided by 7 times 6, so that'll be A0 divided by 7 times 6 times 4 times 3. And so on, A3k plus 1 will be A0 divided by A3k plus 1 times, 3k plus 1 times 3k. Then we'll skip 3k minus 1, then 3k minus 1 times 3k minus 3, and so on. Again, we're taking 2 consecutive integers and then skipping 1 and then repeating that pattern. And this time we end on 3 instead of ending on 2, because that's where this first one started. All right, so at least in terms of those kind of clunky formulas, we've now produced the general power series solution. So y will be a0 times this first series, which will start at 1, right? Because a0 is the constant term, so a0 times 1 will be the first thing that shows up. And then it'll be all these terms, which are multiples of 3. And then the second series will be a1 times, and this time a1x would be the first term that shows up, and then we'll have those other terms, the x to the fourth term, the x to the seventh term, and so on. And then all the terms, which would be like a3k plus 2, those are all 0, right? Because we started at a2 being equal to 0. All right, so let's call this one y1 of x, and this one y2 of x. And let's see. I mean, so this is the general solution, but I guess to be super sure of that, we'd want to show that the Wronskian of these two power series is non-zero. And then we might also want to know what the radii of convergence of these two are, right? On the previous example, we just got the Taylor series for sine and cosine, which we already know have infinite radius of convergence. But these, we might want to figure out what it is. In this case, actually, the radii of convergence are also both infinity. And we'll see a reason for that in a second, besides this ratio test calculation, but we can do the ratio test to calculate it. So, right, if we divide consecutive coefficients of that power series, yeah, you can either have these a0s or not, right? I included them because I didn't want to bother introducing new notation for like a3k plus 3, but with the a0 divided out, right? So in terms of our notation for y1 of x and y2 of x, technically I shouldn't be including the a0, but I don't know. These were the things I already had formulas for, and I didn't want to introduce new notation. It doesn't matter anyway. Like the series, if you multiply through by a0 or if you don't, those have to have the same radius of convergence because you're just multiplying by a constant. Anyway, a3k plus 3 divided by a3k. Right, so the a3k plus 3 coefficient, remember, is like a0 divided by that big complicated product involving like 3k plus 1 times 3k and so on. So that should show up in the denominator when we have a3k plus 3 in the numerator, which is what we have. And then we're dividing by a3k, so now the 3k stuff that would be in the formula for the coefficient a3k will be moved up into the numerator. All right, and everything will cancel out except 3k plus 3 and 3k plus 2. All the terms in the numerator also show up in the denominator. So we end up with the limit as k goes to infinity of 1 over 3k plus 3 times 3k plus 2, and that's equal to 0. And so since the limit of the ratio of consecutive terms is 0, that tells you that the radius of convergence is infinity. Right, so if you remember that ratio test thing from before, if you do the limit of the reciprocal of this, that would give you the radius of convergence. But if you do this limit and show that it's 0, that tells you that the radius of convergence is infinity. If this limit were something other than 0, you would want to be a little bit careful because these are power series involving just like third powers of x. So it's like a power series where the variable is x cubed. So if you wanted the actual, you'd have to take like a cube root to get the actual radius of convergence if it was something other than infinity. But since it's infinity, whether you have a cube root or not doesn't matter at all. All right, similarly, this other series, the same thing will happen. All this stuff will cancel out. You'll just end up with 1 over 3k plus 4 times 3k plus 3, and that will also have a limit of 0 as k goes to infinity. So that also has a radius of convergence of infinity. All right, so those power series will be valid solutions on the entire real line, which is nice. And in order to show this is a general solution, we can compute the Wronskian. And by Abel's theorem, we only need to compute it at x equals 0 because the Wronskian is always 0 or never 0 by Abel's theorem, at least on whatever interval where the coefficients in your differential equation are continuous. But in this case, of course, our coefficients are continuous everywhere. All right, so taking the Wronskian, we only need to look at like the first terms because we're just going to plug in x equals 0 and everything else will go away. So the y1 series starts out as 1 plus x cubed over 6. The y2 series starts out as x plus x to the 4th over 12. So we'll throw in those formulas here and here. All right, when we plug in 0 into y1, we'll just get 1. When we plug 0 into y2, we'll just get 0. And then for their derivatives, we get y1 prime will be x squared over 2 plus higher terms. And when you plug in x equals 0, you'll just get 0. And then y2 prime will be 1 plus x cubed over 3 plus higher terms. So when you plug in x equals 0, you'll get 1. All right, so the determinant is just 1, which is non-zero. So all right, these things have a non-zero Wronskian, so this will actually be, that power series solution we produced is actually the general solution. We sort of knew that anyway because of the fact that A0 and A1 are the initial conditions in an initial value problem, like I said before, right? A0 is y of 0, and A1 is y prime of 0. So at least at x equals 0, we know we can solve all initial value problems. But by Abel's theorem, that says you can solve them anyway. All right, so yeah, we knew the Wronskian was going to be non-zero in advance if you thought of it from that perspective. Because A0 and A1 are arbitrary, that means you can solve any initial value problem at x equals 0. All right, yeah, so that's the general solution. So we can encapsulate some of that in the following theorem. So if you're at an ordinary point, x0, so that means P and Q are both analytic, then you can write down the general solution in terms of power series. And you can always do it like we've done in the previous two examples, where you have the power series A0, the power series coefficient A0 being arbitrary, times some power series y1 of x, plus A1, that power series coefficient also being arbitrary, times some power series y2 of x. And y1 and y2 will both be analytic at x0, so they'll have a positive radius of convergence. And you also know that this Wronskian of y1 and y2 at x0 will be equal to 1. And in particular is non-zero. So yeah, that's what tells you that it's the general solution. And a very useful fact is that the radii of convergence of these two power series will be guaranteed to be greater than or equal to the minimum of the radii of convergence of the coefficients in your differential equation, right? You're assuming that x0 is an ordinary point, so P of x and Q of x are analytic, so they do have positive radii of convergence for their power series. And now you know that all your solutions will have a radius of convergence that's greater than or equal to the minimum of those two radii of convergence. Right, because if you know it for y1 of x and y2 of x, then the same will be true for any linear combination of those two. By what I was saying before, if you take a sum of two power series, or if you multiply a power series by a constant, then the radius of convergence will be at least as large as the radii of convergence of the two power series you were working with. Or will be at least as large as the minimum of the power series that you were working with. But since both of them have a radius of convergence greater than or equal to the minimum of the radii of convergence of P and Q, that'll be the same for all solutions. Okay, yeah, I'm not going to prove this, especially the part about guaranteeing that this radius of convergence is greater than or equal to the radii of convergence of P of x and Q of x. That's pretty hard to prove for sure. The statement about the Wronskian, though, actually, that's just the calculation we've already done. if you do the Wronskian of y1 and y2 plugged in at x0, it'll just be the determinant of the identity matrix again. Because y1 is the solution when you plug in, is the solution to the initial value problem with initial conditions a0 equals 1 and a1 is equal to 0. That will give you the solution y1 of x, right? I mean, if you look at this formula for the coefficients, that's what you get. But these are, of course, also the initial conditions in an initial value problem, like I said before, right? A0 is y of 0, or y of x0, and a1 is y of x, y prime of x0. So that's what gives you this column of the matrix being equal to 1, 0. And then a0 equals 1, a1 equals 0 will give you the other solution, y2 of x. y2 of x has those properties. And so that's what gives you this column of the matrix in the determinant, right? The top right entry will be y2 of 0, or y2 of x0, which has to be, or sorry, other way around. a0 is 0, a1 is 1. y2 of x0 will be 0, and y2 prime of x0 will be 1. Just going by the meaning of these values of a0 and a1. All right, yeah. So that's what tells you the Wronskian has to be 1 for these two functions. All right, let's do one last example. So far we've only done, oh yeah, the thing I was going to comment on, the reason now why these two power series both have an infinite radius of convergence, that actually will follow from this theorem now, because in this case, we just have, in that example, we just had p of x equals 0 and q of x equals negative x. Those both, of course, have an infinite radius of convergence, because they're just polynomials. So that tells you that all your solutions will have an infinite radius of convergence as well. Okay, sorry. So one more example. So far we've only done differential equations with polynomial coefficients. The first one was even nicer. It had constant coefficients. But this method does work even when the coefficients are arbitrary analytic functions. The trouble is things will get a lot messier, and so you're not going to find a nice recurrence relation like we've been finding. That's not going to happen when you're dealing with coefficients that are more complicated power series. So in that case, probably what you're going to try to do is just find the first several power series coefficients. If you used a computer, you could find as many power series coefficients as you want. Computers are good at that sort of thing. And so that would give you like a very good approximation of the solution. But you're not going to get like a closed form formula for all of the coefficients like we've been doing. Okay, so let's find the first three non-zero coefficients of the power series solution about the origin to this initial value problem, y of 0 equals 1 and y prime of 0 equals 0. So now we're dealing with something with a coefficient of cosine x, y double prime plus cosine x times y is equal to 0. All right, so let's get some. So first of all, we know two of the power series coefficients already. A0 is 1 and A1 is 0. That's just reading off from the initial conditions, like I've been saying. A0 is just the value of the function at 0. A1 is the value of the first derivative at 0. So A0 is 1 and A1 is 0. All right, so that means we have this formula for our general power series about the origin. So it starts at 1. We skip the x to the first power term because A1 is 0. And then we go on to a2x squared plus a3x cubed and so on. So the second derivative will be 2a2 plus 6a3x plus 12a4x squared and so on. And then the first few terms in the Taylor series for cosine x, we have 1 minus x squared over 2. The next one would be x to the fourth over 4 factorial, right? We just saw that formula in the first example, but we should only need these two terms in order to get the first three non-zero coefficients that we're looking for. So you can always just start with a handful of terms, and if you realize you didn't have enough, you can just throw some more in. Not a big deal. All right, so let's plug everything in. So this is the second derivative. This is cosine x, so it starts with 1 minus x squared over 2. And that's the series for y, at least the first two terms of it. So we have 1, and then we don't have an x to the first term, and then the next one's a2x squared. All right, so you can see the reason why we're not going to be able to get like a closed form formula for all of the power series coefficients and some nice recurrence relation is because we're multiplying two power series together here. This will be the product of two power series. And like I said, the product of two power series is a power series, but the coefficients in that power series are just going to get more and more complicated, right? So if you think about it, it's like multiplying if you think about multiplying two really big polynomials together, right? You're going to get a ton of terms, right? If you multiply two polynomials with n terms each, then you'll have n squared terms total. But the degree of the polynomial is only 2n. So you're going to have like several coefficients in the product polynomial are going to have like a bunch of complicated terms in the sum from when you multiply them together. All right, yeah. Well, let's just see what happens at least for the first few terms, and then we'll see how it can get more complicated in the future. All right, so let's collect the terms of various powers of x. And just like before, then we can, because we know the whole power series is equal to 0, we know that all the coefficients in the left-hand side have to be equal to 0, as long as we make sure we've collected everything together. All right, so constant terms. We have a 2a2 here, and then we'll have a 1 times 1, which will be 1. So we'll have 2a2 plus 1. That's the constant term. Coefficients at x to the first. We only have one of those. That's this term, 6a3x. Because cosine x and our series y both are missing an x to the first term, there's no way to actually get an x to the first term from their product. All right, but x squared will have a lot of terms. So first we'll have 12a4x squared coming from y double prime. Then we'll get a positive a2 x squared coming from 1 times a2. And then we'll have a negative 1/2 x squared coming from minus x squared times 1. All right, so those are those three terms. All right, so we'll see we get two terms in the product for x squared, right? So the constant term, there's only one term in this product. That'll give us a constant term. X squared will have two terms in this product, but something like, let's see, x to the 10th, you'd have something like an x to the 8th term times an x squared term, an x to the 6th term times an x to the 4th term, and an x to the 10th term times an x to the 0 term. But you can like switch which one has the 4 and which one has the 6 and so on between each of them. So x to the 10th would end up having like 6 terms in this product. And so you can see for like x to the 100, you'll have a ridiculous number of terms showing up in that product. So there's no way you're going to get some like closed form recurrence relation, because you're just going to have an absurd number of terms popping up when your exponent on the x gets large. All right, but in any case, we were only looking for the first three non-zero terms, so hopefully we're fine. We already have one of them, so we just need two more. So hopefully between a2, a3, and a4, we'll be able to get two more which are non-zero. All right, let's see. So first we have, from this one being equal to 0, that tells us that a2 is minus 1/2. This one equal to 0 tells us that a3 is 0. All right, so a3 was not a non-zero coefficient, but hopefully a4 will be. And to figure out what a4 is, we will set this one equal to 0. So that'll tell us that a4 is minus a2 over 12 plus 1 over 24. And then we use the formula for a2. a2 is minus 1/2, so minus a2 over 12 is positive 1 over 24. So we have 1 over 24 plus 1 over 24, which is 1/12. All right, so yeah, we did indeed find 2 more non-zero coefficients. So we have the first 3 non-zero coefficients. It'll be 1, minus a half, and then 12 on the 0, 2, and 4 terms, respectively. So our power series solution to this initial value problem will start out as 1 minus x squared over 2 plus x to the 4th over 12. And so at least in a small neighborhood of x equals 0, this will be a pretty good approximation of the solution to that initial value problem. All right, I will stop there. Here are the quantum formalism links, and this is the final lecture. So that'll be it for me. I hope you all enjoy the rest of the course.